It began as a brilliant burst of light, too distant for the eye to see, but powerful enough to punch through the vast emptiness of space and touch our world in an instant. On May 14th, 2025, as dawn broke across different corners of the globe, the sun, that seemingly steady beacon in our sky, reminded us that it is anything but tame. A colossal X 2.7 class solar flare erupted from sunspot region AR4087, releasing a surge of energy so immense it reached Earth within minutes, disturbing the invisible threads of our communication systems and wrapping parts of the world in sudden, unexplainable silence. For most people, that morning felt like any other. But in aviation control towers, aboard ships navigating international waters, and inside emergency operations centers, something was going terribly wrong. Radios went quiet. Signals flickered. Entire networks that millions rely on every day simply vanished. Europe, Asia, and the Middle East were thrust into a kind of disoriented hush, where systems failed not from human error or mechanical breakdown, but because our star had spoken, loudly. The flare, categorized as X 2.7, wasn't just a statistical anomaly. It was the strongest solar event of the year so far. These flares are ranked by their intensity, with each step up in class multiplying the power by 10. X class is the highest, the most violent, the most unpredictable. A 2.7 rating means this was nearly 3 times more intense than a base-level X1 flare, a level already considered severe. It came from a sunspot that had been rumbling with tension for days, releasing smaller flares on May 13th and even earlier the same day. The sun had been restless, its surface alive with the kind of energy that makes scientists lean forward, anxiously watching, listening, waiting. The energy released by that flare raced across the 93 million miles separating us from the sun at the speed of light. It slammed into our upper atmosphere, a wave of high-energy radiation that ionized the very layer of air responsible for carrying radio signals across long distances. This invisible disruption occurred in the D layer of the ionosphere, a critical zone for high-frequency radio waves used by pilots, navigators, and responders. Suddenly, those waves couldn't penetrate. Messages that should have traveled thousands of miles were lost. Flights had to reroute. Emergency teams scrambled to reestablish contact. It was a glimpse, brief but chilling, of just how vulnerable we are when the sun lashes out. But here's the part that unsettled scientists even more. The flare wasn't accompanied by a coronal mass ejection, at least not one directed toward Earth. That might seem like good news, but it's not necessarily a reason to relax. CMEs are huge clouds of solar plasma that can take hours to days to reach us. They carry magnetic fields and matter capable of disrupting satellites, GPS systems, and even electrical grids. The region that produced this flare, AR4087, is still rotating. It's still growing. It's still active. And as it turns to face Earth more directly, the chances of a CME heading our way rise significantly. Imagine it like this: a lion pacing just outside your window. It roars, shakes the walls, then disappears behind the trees. But you know it's still there, and it's not done yet. As this flare struck, the consequences rippled outward. High-frequency radio blackouts across 3 continents weren't just an inconvenience. They were a demonstration of just how quickly space weather can disrupt modern life. Think about the chain of reliance we all live within. Planes talk to towers. Ships call ports. Emergency crews coordinate across vast distances. When solar flares like this one explode, they don't just make the sky shimmer with auroras. They break the links in those invisible chains, one by one. And these effects didn't just stop with radio. Satellite operations were at risk too. Even though this event didn't trigger a CME, the increased radiation altered the ionosphere in ways that could skew GPS signals, throw off navigation systems, and even tug satellites out of their carefully plotted orbits. The atmosphere swells slightly when hit with intense radiation, creating more drag for satellites in low Earth orbit. Over time, that drag can shift orbits, compromise instruments, and increase the chances of collisions. We often talk about Earth as an island in space, but what we rarely admit is just how thin the shield around that island really is. A solar flare, traveling at light speed, can breach it in minutes. A CME, if directed, can follow with a knockout punch. And in 2025, we're walking into the peak of the sun's activity cycle, solar cycle 25, with our world more wired, more connected, and more dependent on delicate systems than ever before. This flare wasn't just another hiccup on the sun, it was a warning. A R4087 had already shown it could erupt with significant force. And if this flare was the beginning of a pattern, it could very well signal the early stages of a much larger storm. A storm that could test the resilience of every satellite, every power grid, every communication line linking us together. The scientists tracking solar activity know this dance well. They've seen it before. During the Halloween storms of 2003, for example, when geomagnetic disturbances knocked out satellites and power grids across the globe. But the stakes today are even higher. The infrastructure we depend on isn't just more complex, it's more fragile. It's built for precision, not brute force. And the sun, as we were reminded on May 14th, does not play by human rules. Still, even with all our advancements, the most humbling truth is this. Our ability to predict these events remains limited. We can spot sunspots. We can observe flares. We can model potential CME paths. But when the sun erupts, it does so without warning. It does not blink before striking. And yet, that flare on May 14th did more than cause chaos. It pulled back the curtain on a vast and ancient power. It reminded us, just for a moment, that we are still very small. That all our satellites, all our systems, all our interconnected wonders, they all depend on a star that burns with no regard for our plans or our precision. The morning after the flare, something strange lingered in the air, a kind of tension, like the quiet hum before a storm that hasn't yet passed. Around the globe, emergency response systems scrambled to piece together what had just happened. Commercial airline pilots reported brief losses of signal, and air traffic controllers in several countries experienced momentary dropouts in high-frequency communication. For those depending on these systems, especially in transcontinental flights skimming over polar routes, this wasn't just an inconvenience. It was a glimpse into how thin the veil of our technological resilience truly is. Across Europe, Asia, and the Middle East, technicians in radio stations, military command centers, and cargo shipping hubs all dealt with a sudden, jarring silence. High-frequency radio bands, the lifeline of long-distance communication in regions far from fiber optic coverage, had been swallowed by the sun's fury. The ionosphere, that fragile, invisible layer that protects and enables so much of our global communication, had just been blasted by a torrent of X-rays and ultraviolet light. The D layer of the ionosphere, normally a quiet absorber of daytime signals, became over-ionized, thickened like a sudden fog, and choked off radio waves in the 3 to 30 megahertz range. It was not the kind of damage that knocks out satellites or fries transformers, but it was enough. Enough to make the world pause, to remind us that all our networks, our navigation systems, our digital lifelines are strung together across an incredibly delicate balance, one that the sun can disrupt in less time than it takes to blink. In space, satellites orbiting in low Earth orbit encountered a different problem altogether. The atmosphere had swollen ever so slightly, an invisible balloon expanding outward from the heat of the flare. This increase in atmospheric drag nudged satellites ever so gently off their paths. It's a subtle effect, but even millimeters can matter when you're dealing with tens of thousands of miles per hour and billions of dollars in equipment. Operators were forced to monitor for any course deviations, to account for the slow, creeping friction that could, over time, destabilize their carefully plotted routes. And then there was the potential threat that still loomed, what hadn't happened yet. That's what kept scientists at solar observatories across the world awake deep into the night. The flare that struck on May 14th was powerful, yes, but it had not produced a coronal mass ejection, or CME, aimed directly at Earth. A CME is a much slower, bulkier monster, more like a solar hurricane than a lightning bolt. When one does hit, it can trigger geomagnetic storms strong enough to rattle our planet's magnetic field and wreak havoc on everything from power grids to communications satellites. And the sunspot responsible for the flare, AR4087, wasn't done. It had already produced two other strong flares in the previous 24 hours, an X 1.2 and an M 5.3. The pattern was unmistakable. A R4087 was building toward something, and as it continued to rotate toward a more direct Earth-facing orientation, the chances of a CME making a bullseye hit only grew. There was an eerie familiarity to this. Scientists and sky watchers remembered what had happened just a year earlier, May 14, 2024, when sunspot region AR3664 produced an X 8.7 flare, one of the most powerful solar eruptions in modern history. That flare did produce a CME, and the result was a G5 class geomagnetic storm, the highest level possible, the kind that sends auroras dancing across skies usually untouched by them. That day, people in Spain and Texas looked up to see brilliant green and red waves overhead. Stunning, yes, but underneath that beauty, chaos. GPS signals scrambled, shortwave communication dropped, and airlines rerouted polar flights away from high radiation areas. It was a glimpse of what solar storms can really do when they carry not just light and radiation, but mass and magnetic fields. And it was a lesson that most nations were still digesting when the flare of May 14, 2025 struck. This time without the mass, but not without the message. Meanwhile, space agencies turned their eyes toward the horizon of the sun. A R4087 loomed like a thunderhead, churning with magnetic energy and dark, tangled filaments across its surface. Observatories like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter watched every shift in its posture. The Parker Solar Probe, the daring craft that dives closer to the sun than anything ever built, was already delivering fresh telemetry about the solar wind speeds and magnetic field variations that hint at coming eruptions. These spacecraft don't just observe. They're part of a vital early warning system, a sort of solar seismograph that helps humanity by a few precious hours or even days before a CME might strike. While solar flares hit Earth almost instantly, CMEs, traveling slower, allow time for grid managers, airline controllers, and satellite operators to brace for impact. But prediction is still part science, part gamble. Not every flare launches a CME, and not every CME is earthbound. Understanding which ones will be catastrophic and which ones will simply pass us by is still one of the great challenges in space weather forecasting. It's like watching a storm form far out at sea, with no radar, and trying to guess which way it will move, how fast it will travel, and how hard it will hit when it finally arrives. Governments and private industries are waking up to this reality. In boardrooms and conference halls, engineers are talking about transformer shielding, satellite redundancies, and new types of hardening protocols for space assets. It's not just about designing stronger machines. It's about building a more resilient civilization. A civilization that knows its lifeblood is invisible, fragile, and vulnerable to the whims of a sun that's 93 million miles away. But beyond the machines and the protocols, there's something deeper at stake. Solar storms don't just threaten our infrastructure. They challenge our sense of control. They remind us that we are not separate from the cosmos. We are inside of it. The Earth doesn't orbit a quiet, benign furnace. It orbits a wild, living star, a star that breathes and lashes out, and sometimes makes us look up from our glowing screens and remember just how small and breakable we really are. And so, as the world watched and waited, May 14th became more than a flare. It became a warning, a line drawn in ultraviolet light, a whisper from the sun that it's not finished yet. It was now May 15th, and despite the initial flare having passed, a collective tension still gripped the scientific world. The sunspot, AR 4087, massive, volatile, and still rotating into prime position, was nowhere near finished. In fact, it had grown. Magnetograms revealed an even more complex mix of opposite polarities, locked in tight magnetic knots. These were the exact configurations that breed instability, that birth flares and launch coronal mass ejections like cannonballs from a charged battlefield. The sun was restless, and Earth was directly in its crosshairs. While the general public returned to their routines, scientists at NOAA's Space Weather Prediction Center and other observatories stayed in emergency mode. Each new image from the Solar Dynamics Observatory added urgency. The next flare, if it erupted with the right magnetic orientation, and worse if it launched a CME, could be the kind of event that reshapes infrastructure, policies, and priorities. Deep in an underground control center in Colorado, specialists from multiple agencies gathered for a joint briefing. On the massive digital displays above them, simulations ran on loop. CME propagation models, geomagnetic impact forecasts, radiation dose maps for astronauts aboard the ISS, and satellites in geostationary orbit. A new flare was imminent. The signs were all there. Brightening in the chromosphere, sudden increases in soft X-ray flux, filament oscillation, and then at 3:12 UTC, it happened again. An X 6.9 class flare ripped through the darkness of space, brighter than anything AR 4087 had produced before. This one did come with a coronal mass ejection, and its trajectory, at first uncertain, soon became the one thing everyone feared: a direct hit. The CME was fast, clocked at over 1,500 kilometers per second, and highly magnetized. It was the kind of event that could compress Earth's magnetosphere to half its normal size. Within minutes, warning alerts went out through international coordination networks. Power companies were told to brace for geomagnetic-induced currents, those invisible surges that can overload and destroy transformers. Airlines began to reroute flights, again avoiding polar routes, not just for signal disruption, but to shield passengers from increased radiation levels at high altitudes. In Earth's orbit, satellite operators scrambled. Instructions were beamed to dozens of satellites to switch to safe mode, reducing surface area to incoming particles, turning off non-essential systems, and reorienting solar panels. The International Space Station, with its exposed human crew, took shelter in the most heavily shielded sections of the craft. For the astronauts floating just a few hundred kilometers above us, the event was not theoretical, it was personal. As the CME approached, Earth's magnetic field shuddered. A shock front struck first, triggering a sudden impulse. Then the full brunt of the magnetic cloud made contact. Geomagnetic storm conditions surged to G4 and then G5 levels. Auroras once again ignited the skies, but this time even farther south than before. People in Mexico, southern Japan, and even parts of North Africa looked up in awe at skies painted green, purple, and crimson. But beneath that beauty came the consequences. In Quebec, parts of the power grid flickered as reactive currents swelled across long transmission lines. Transformer substations experienced overloads, and automated systems kicked in to isolate and stabilize key nodes. It worked, but barely. In other regions, smaller disruptions compounded. Communication outages spread through high-frequency bands. GPS accuracy dropped dramatically. For a time, commercial ships in the Pacific Ocean operated effectively blind to their exact coordinates. In the digital domain, the storm wreaked quieter chaos. HF radio networks collapsed. Some low-orbit satellites reported radiation glitches, causing temporary data corruption and loss of telemetry. The radiation storm that followed the CME, filled with high-energy protons, triggered additional alerts for aviation crews and satellite operators. The Van Allen belts throbbed with particles, overwhelmed. Meanwhile, one of the most subtle but ominous effects unfolded invisibly in Earth's upper atmosphere. As the geomagnetic storm intensified, the thermosphere heated and expanded again, more severely this time. Satellites that had only recently been repositioned were now dragged down by atmospheric friction faster than expected. Tracking teams at NORAD recalculated orbits in real time, issuing bulletins about possible re-entries and collision risks. It was like playing cosmic billiards, only now the table was shifting beneath the balls. The storm lasted for nearly 36 hours, subsiding only after Earth's magnetosphere began to absorb and dissipate the intense solar wind pressure. When it finally ended, the Earth had weathered the impact. And in the aftermath, something changed. Not just in the technical manuals and satellite protocols, but in people. Governments were suddenly speaking more openly about solar threats. Emergency drills were discussed. Power grid operators reviewed worst-case scenarios. International cooperation became more than a formality. It became necessity. At the same time, average citizens, those who had looked up to see lights in the sky that weren't supposed to be there, began asking questions. What if the flare had been stronger? What if the magnetic fields had aligned differently? What if the CME had struck at just the wrong angle and triggered a cascade failure in power infrastructure? That's when attention turned again to history, to the Carrington event of 1859, the solar storm that set telegraph lines on fire and shocked operators from thousands of miles away. If a storm like that struck today, modern estimates suggest it could cause up to $2.6 trillion in damage globally, crippling infrastructure for weeks or even months. May 2025 hadn't been Carrington, but it had been close enough to show us that it could happen again. And it had been enough for policymakers to listen when scientists said, we need to prepare. Because the sun, while life-giving and beautiful, is also a source of chaos, a dragon of plasma and magnetism, breathing fire across space in unpredictable bursts. By the end of that week, AR 4087 had rotated away from Earth's direct line of sight. The threat had passed, for now, but a new understanding lingered in the minds of many. Our technology had advanced, yes. Our satellites were smarter, our grids better protected. But nothing we've built is immune to a star's wrath. We ride this planet like a ship on cosmic tides, vulnerable to a sun that doesn't notice us and doesn't need to. So when the next sunspot forms, and the next flare erupts, and the next CME barrels toward Earth, we will remember May 14th and 15th not as isolated incidents, but as omens, as signs that we are not above nature, we are within it. And nature, especially at stellar scales, does not ask permission before it acts.